This is where the magic happens. 1,000 times. We tell the lexer, give me a token. There we go. We will be seeing everything we parse.
Hey there.
Welcome to Lil is a Language. This is my compiler. It's a language for making video games, and it's nowhere done. It's work in progress, so please bear with me. Everything is work in progress. Nothing is done and set in stone or anything like that. And this is my hobby. I'm actually the owner of an indoor skate park. That's my business, and I'm doing this programming thing out of pure joy of I like programming, and this is fun, and this is what I ended up doing. I've been designing, so to speak, a language for 10 years now. This is the result of my tinkering with something like a language for all my life, and here we are. So let me show you what I've got. This is a function called myfunc, and it contains a typical hello world. Let's run this. We're in this folder where this text file is. Lil is the command, is the tool. It's a command line tool. And we're saying the file name now, main.lil. There you go. Here's our hello world. So what is happening here? Here's the start of our main function. The first thing we do is we look at the arguments that were passed in. If they are some hard-coded values, we handle them in these cases. And everything else gets put into this arguments array. It is read as lil code. So actually what comes after the minus minus is read and then put into as a string into here. And if it doesn't match the minus minus or one of these, then it's the file name and we set it here. And then this is one of the big first important classes that I want to show you. It's a build manager, which means it's like the owner of different objects which make up the whole project. And each of these objects are like one of the lil files that you write. And then the linker at the end puts it all together. And then we have these 3 stages here. In the read stage, what we do is we read all the lil files that you write, and we only extract out of them the configuration that we want. Then we set them, and then we use those in this third phase where we read everything again, but now with the configuration set to the actual values we want to use. So I want to show you now the configure defaults. This is a file that will be included with the download when you download the compiler. And we can see it's like some default stuff, so we can start working even if you don't set any configuration. For example, the build path, it needs to know what name to give to the folder it wants to build the temporary files in. Whether you want to compile actually or just print the representation of it. In here we have different configurations. For example, when we run in debug mode, we want to have a lower optimization, and when we working in release mode, we have a higher one. And here we know different configurations that are specific to the platform we're working on. Like Windows and Linux are not done yet, that's why they're so small. But I'm working on Mac, and you see like I'm setting a lot of linker flags, and I'm executing commands for the platform layer over here. And yeah, I mean, there's a lot of things to do. It works. It creates an XML file with the plist file, and it makes the directories with the resources, for example, in here. This is all Mac specific stuff. In Windows, like it would work different. So let's go in here. We are in the build manager, and like in here, we initialize a string with the contents of the file, and then we give it to a code unit. A code unit is like one object file, and this is represented in here with this class. And in here we give it a string, so it can give it to the parser, and we run it. So let's do that. So we have a couple phases again. We have build AST, which is the abstract syntax tree. And this is like a representation in memory with objects that are structured in a way like a tree. And this represents all the nodes in your code. Like, for example, a function, this is all of this, contains then the name of the function in here, and it contains all the expressions that are contained in the body, etc., etc. So this is all like nested inside of one another. That's why it's a tree. And then we have some transformation passes, and this is the standard, but we do sometimes run different passes when we are importing one file inside of another. We also add at the very first file standard lil library, so we get like strings or arrays, dynamic arrays, and stuff like that automatically built in. In this function, we tell the parser to go parse the string. So let's look at that. We have a lexer, which is a piece of the parsing mechanism that takes a look at every character and makes very, very, very basic blocks out of them. So we have, for example, this is a keyword, so to speak, but for the parser, first it's just seeing that these are like characters and this is a word. So we have like an identifier. Then we have a white space, then we have another identifier. Then we have white space again. The basic idea is like the lexer reads characters and the parser reads complete tokens. Tokens they are called. So that's why we have the read next token. So we tell the lexer, give me a token. If the character is an ASCII character or an underscore, we read an identifier. Some cases we have set the compiler to also read hexadecimal values which can start with a letter. Anyway, if it is a space, we read white space. If it's a digit, we have again hexadecimal numbers, or we have percentages. Then we have other symbols. Yeah, and if it can't find anything for it, it goes into here, which is an invalid char. So in our case, we go to the identifier. This loop reads all the letters and stores it in a temporary string until we see that it's like a white space or something else. And then it gets out of the loop, and this function, extract current token text, will give you the results of everything that has been stored. And then we make a token out of it and we return it. So we have the token over here and we update the current token. All right, let's go back one again. We're here in parsing. So we have the token. So the first thing is the token, like a word. It says fn. So this is the meat of the thing, the parse next function. This one is very important. In here, we look at the current token. This is where everything starts, like when we read anything lil, just top level. We say, I don't know anything about any state, any context, anything. You just parse next. So there we go. And in here, we have this check. This looks forward and sees if what you are doing is defining a rule, which we'll see later, or if you're doing something else. In this case, this will not match, because this is like defining a function. So it will read an expression. And once it has read this expression, it commits it. This is like, all right, we have this thing, and now we pass it off to some receiver, which is another class that is separate from the parser that will do something with it. For example, it's different when you want to just colorize a code. then you could use this parser with a different receiver, that when each part of the code is received, then it just builds a string with different colors to be output as HTML, for example. I have actually done that. And then we can reuse this parser without having to like copy and paste and modify it for a different use. You can just plug in a different receiver, and in this case it's a receiver that builds the abstract syntax tree. In other cases you can just write out a string, for example, but in this case it takes the expression that we read and we commit it to the receiver. Do something with it, please. But let's just look at the read expression one. What happens in here is usually like it gets into here where it just starts to read a single value. So this is a function declaration. When it comes to this part, it will see that the token text is fn, and it will say, yes, this is a function. If we read the function type first, then we do this, but we're not doing that right now. Like right now, first we say like read this data, this string, and then the next part, like we skip over the white space. I have an idea. Let's go with the debugger. Let's run this in here. There you go. We received the fn keyword. So now you see the output down here. There we go. We will be seeing everything we parse as it appearing down there. So we have the white space, and now we have an identifier, and this is the name. So now we initialize the next token, but now I want to go in here. So you see this receive node data. This is the AST builder. This is this receiver I was talking about earlier, and node data is like the texts of each node, and then after this is read, like it will receive the parsed node, the abstract representation. But this, for example, is where it is receiving every string part of it. And now we go in there. Let's just look where this takes us. So we are in a function declaration and we're receiving the function name. So on this function declaration, we now set its name, and the data, you can look at down here, is myfunc, which is the name that we are reading here. So this is like this node of function declaration, this whole thing. In here, the AST builder has like this temporary node that it's working with, and then it sets its name because it puts it together because this is being received from the parser, and then it sets it on this node. It sets it over here. We read the next token. So now this is what I wanted to show you earlier. So now we don't have any function type, so this is valid. We can read the whole block. I go in here. It's a function call. We read that. Do we have a semicolon? Yes. Then we skip over it. So we're done. Out of the loop. And back to the read function. So now, end of the function is a block close, which is expected. Else it will raise an error. Okay, so now we read one single value. And in here, can this have more parts of this expression? No. So it's a single value of this type, single value node type, which is function declaration. So we set these and return this state, which is valid. All right, so everything's good. We are in a valid state and we read the expression. We skip over any white space 1,000 times, and then we commit the expression. Let's go there. So this is again the AST builder, which the receiver of the parser. And then in here we have it keeps track of the root node. The root node is like the top of the tree which contains everything we put into the file. It doesn't actually exist in the code. It's just like there is this one node which holds everything else. It's called the root node. And we add whatever we had, we add it to it. And it will do stuff depending on what you give it. So if you give it a function declaration in this case, you add it to node tree. So it adds it to every node in the Lil compiler. This is like an abstract superclass in C++. It has this child nodes vector, and we add this node to this child nodes vector. Now we also set the local variable, which means the name of the function, myfunc, is available in the namespace that you're working in. So that's why it's set as a local variable, so you can access it. And then we parse again. And this time we parsed the call to myfunc. And it is done. So now we run the passes. Let's go there. We have a list of passes in this vector, and we add them. First is the argument resolver. This will take these kind of things, which is a hashtag arg. This is an instruction, it's called in Lil, and this will be turned into the corresponding thing that you give it from the command line. And if you don't give it a thing, then it will take the value from the default part. So for example, isMain, when it runs through the argument resolver, here, this guy, then it will see you haven't said anything about isMain, so we just turn all of this into true, like this. The same happens with the config instructions. So if you have one of these, then you want it to be replaced with the actual value that comes from the config. This one turns hashtag numbers, and it's this color in the same format as CSS or Photoshop, and it's hashtag and then a series of numbers. So that's a color, and it turns it into an actual text code of how you would define a color, like using objects in code. We'll see that some other time. The preprocessor, this is one big part of the whole compiler. The preprocessor takes other files and puts them into this one file. And also it works with the snippets and pasting snippets inside of other parts of the code and stuff like that. So it's like a deep transformation of your code that happens at this stage. You see all the instructions it handles: needs and import, if, snippet, and paste. All of these are handled inside the preprocessor. Then we have a validation of the AST. This is not like validating everything, but it's just validating whether it makes sense which node is put into what. Not exactly what the node is saying. For example, if you have a variable that's misspelled, it wouldn't catch that error at this stage, because it's not concerned with is this semantically correct, but only is the syntax correct. All right? Well, anyway, I'm not going to describe everything because we're not going to finish, but like it does transformations and it checks stuff, and like it does a lot of things. I will go into detail in another video, because this is a lot of information. I'm seeing like I'm taking forever here. At the end here, the type validation. This one is the one that catches whether or not the variable actually is a valid name. It knows about the local variables and then checks. So we execute all the passes. They all have been added to the list of the passes, and we just give it to the pass manager, which will execute each one of them. It's like a fancy for loop. but it has some context, and it knows some stuff that will, yeah, it does a little bit more. But anyway, it does all the passes and then it deletes them again. Since we are creating each one of these with new in here on the heap, then everything in this array needs to then be deleted again at the end. And then that's how we keep memory leaks from happening. All right, so this is the run passes, and this is the end of the run function in here. Anyway, let's just go over there. Right now we were just talking about one file, the main code unit it's called in this case. Everything that you add to it, that you link together, needs to be compiled as well. So for example, if in here I say needs some other file.lil, all right? So this would be the way I say that I want the compiler to compile this file as well and then link them together at the end. So it's not like that there's this other one, import. So this says, take this file and paste it in here. Put these files together as one code unit into one another. But the needs one says, compile this one file as some other code unit and then link them together at the end, because I don't want everything to be mashed together. What I want is, like, this is equivalent to in C having a header and then including other file.h, which would be the header which contains the definitions of the functions we want to call. Long story short, we have the other files. So if it's not the case that we're saying, okay, just compile this one single file, but this is default that it's not, then we go in here and we say, for every file that it's needed for this build, then we go ahead and compile this as well. So this happens over here, and we make a code unit for it like we did for the main file. So we run it as well, and then it's an object file. We emit it with this guy over here, the output emitter, which it uses LLVM to create an object file. We have the linking step here, like this on Mac uses the system linker, which is called LD, and then we give it the path and the thing, and then it links it all together into an executable. This is how it at the end it gets turned from object files to the executable, the final binary. This is where it happens. This is where the magic happens. Linking. And then we have the result, and I'm calling it packaging. This is where it puts it all together into the final folder where it needs to be. Like in Mac, it needs this very specific structure where the folder, the outermost folder, is called .app at the end, and then contains these folders inside. That what was set in the configure. And now if we have enabled the option to run it, like we get the configuration here, and if it's true, then we go ahead and run it in here. Oh yeah, now I catch some errors. You see, at the type validation stage, it said, oh, we have this function you're trying to call, but it's not defined anywhere. So let's remove this. Hello world, there you go. So we can look at the output here. It's quite a lot of text that gets output. So we have the configuration we're using. We have the name for it is main. We have the build steps that will be executed in the build phase. It automatically will create the main function for me. We can disable this if we want to add like a little code into another project where the main function lives, or if you want to have your own main function, this can be disabled, which is really nice. But it's also nice that it gets done automatically when you don't want to think about it. For example, when learning about it as a beginner. We have the path for the standard Lil library files, etc. We parse the file, and this gets converted into this syntax tree. So we have automatically import the init, which is what contains the main function. And then we have this constant that got added, which is that we are in a debug build, which is the default. And we have the constant that we are on a Mac. And now we have this actual first node, the function myfunc, which is described here, function declaration with the name, and then it contains in the body these other nodes, which is a function call, which with argument is a node inside of the node, which is a function call. And then the initializers are the top level code that gets stored apart in this list, and it's call. And then here we don't have anything to do. We don't have anything to do either, not here. Here, processing. We import, we take care of this instruction. So we do that. I don't want to explain all of this. Let me just quickly go to where this ends. So, end of file, init. From this, we have the lil init function. We have the main function, which now calls the init function. And we have this snippet here, which is the initializers are now inside here as a snippet. Here, it went through all the stages, and this is the end result after the last transformation. So we have the main function, which calls lil init. Lil init in here is the initializers. So this is the call to my function. So from here it goes in here, and this calls the function that we have defined, my function, which contains the call to the print function. This is, I can show it to you. So lil.lil, this is what gets imported automatically, and it gives you functions from the C standard library, array, dynamic array, strings, and this is the print. So in here, this is the print function, and it has this argument, which is a variable with multiple types, and then there is this optimization which turns these kind of functions in individual functions for each one of these types, and then it transforms the call to them into specific calls of this. And then each one of the functions will contain the specific parts it uses. So for example, when it's bool, it will take this part, and when we do what we did, which is a string, then it does this. It uses the puts function from the C standard library to output. Well, actually, that is what it does, but in this case, we have overridden the print file for Mac specifically, in which case it does an Objective-C call, because this is what the system wants, that you log things with the nslog function, which takes ns string. So we do that, and we build an ns string from this UTF string, which is a C string, and then we give it to it, and then that's why when we print this, it also has this stuff in front of it, because this is using the nslog function, which automatically adds the timestamp, and it also makes it available for the application of the system that it's called, I think it's called console, this one. So if you just put it, if you're using the C version, this one, it doesn't appear in the console, but with the nslog version it does. But anyway, what I wanted to show you is that in here, this print function is actually this print function. This is the LLVM IR representation, the intermediate representation. And the funny thing is, this is actually the same language that C and C++ use as an intermediate language before it gets converted into assembler and or a binary file. And that's why, and also I'm using the same calling convention. That's why when you use Lil code, it's basically like if you were writing C code, because it's interoperable, it uses the same calling convention, and it gets compiled into the same intermediate representation. That's why at the end you can link it all together, and the system doesn't even know any better, you know? So this is the intermediate code that gets written, and you see how this is much harder to read, and it's lower level. But this is what my language gets transformed into. So actually, if you think about it, the whole compiler, what I've done is actually just sort of like a string processor, which takes my code and transforms it into this other code. And this other code, I'm using Apple's LLVM for this, which is excellent and has a very long history and it's been actively developed and everything. It has a big community. I'm really glad I chose this. And this is what it gets used to then transform this into the object file and linked together into the executable in the same way a C and C++ file would. So I'm not doing anything special there. I'm using the existing infrastructure and I'm only writing my own front end up to the point where I can hand it off to LLVM and then say, okay, now turn this into ones and zeros for my CPU. And I don't have to know exactly how to choose the registers or how to do exactly how each transformation pass for the optimizations that they support. But I can use all this incredible engineering effort, which is open source and free to use, and I'm really glad for it. And I'm making my part as well. So I'm building this front end for LLVM, which makes these intermediate representation and then builds these output files, links it all together, and then creates this final binary. So let me show you one final trick. If I, instead of doing this, I define something, for example, I'm saying like this, and my background should be blue. So this is the part that it's like CSS on super powers, so to speak, because you have seen like I've executed functions, I've done stuff with variables, I've done a lot of programming stuff. But there is this whole other side, which is like CSS, where you define a rule, where you have a selector, where you say what, and then you give it properties with what property and what value. And you don't care about how it exactly happens, you just define its values. So now the syntax is much, much cleaner. And this would be like the front end of my language, and then is the back end is where you do all the low-level computation and all the things, and just expose your stuff to this other side, which is declarative. So you can have like the designers working on the code from this part, which who don't know how to do hardcore low-level programming in the same language that the ones that then write the library and try to make everything very efficient, and then give access to the designers which who also use code, but in just a very more limited manner. Well, anyway, I'm talking too much right now. I just want to show you that with this way, when I run it, now it will build an application and it will launch it, and it will contain a window. There you go. Here we have the window and the size we said, and then the color with the color background. And we have even a menu with the name of the app, and we have this quit menu entry. I will show you in another video like how to configure all this, how to use this, put stuff into this window, and etc. This is like really fun. I just wanted to show you a tour of how to go from the source file, which is this text file, which gets read into this command line and then gets turned into an abstract syntax tree, gets processed, then gets through LLVM, gets turned into an object file, and then linked together and then create an application. That's the infrastructure I have. That like you can see, you don't need like the separate build system or something like that. Like you use this tool, you give it a source code, and it will build the application for you. So I hope this has been entertaining. It has been really fun for me, and I would like to leave it here for another day. You can follow me on Twitter at veosodano. Follow me here. Follow me here. And I will be making YouTube videos, and I will try to stream a lot. I hope this has been good for you, and it has been for me, and I hope to see you next time. See ya.